All right, mathematical patterns, and I brought a timer because I know the bell was going to catch me off guard. 36 minutes of speed teaching. So mathematical patterns, we're going to identify mathematical patterns found in a sequence. A sequence is just a listing of numbers, and hopefully, we'll see the patterns and be able to go through them. Don't worry if you're one of the people that it doesn't instantly come to. It's okay. As we go through things in this chapter, you'll realize, well, I don't need to be one of those people because there are formulas that I can use. And we want to build some formulas here and be able to use formulas to find what's called the nth term of a sequence. The nth term of the sequence is when you say, I want the third term of the sequence. I want the fifth term of the sequence. And you only want one. You don't necessarily need the whole thing. And what we're going to learn is there are two different types of ways to write sequences. The first is a really methodical, explicit formula, and that's exactly what it's called, an explicit formula. Explicit means you do exactly what you're told to do and everything will work out right. An explicit formula would allow you to find the 1050th term if you needed it. But then we'll also talk about recursive formulas, which wouldn't be good for the 1050th term, because to do recursive, you need to use the first term to get the second to get the third to get the fourth to get the fifth. And to get the 1050th term, you'd be there a long time. So two different types of formulas, both can have their uses, but we just need to start off with some raw patterns here, folks. That's what we have to do. So this one says, for each figure, how is the number in the center of the tile related to the numbers on the other tiles? And then it says we could go on and talk about what will be the center number in figure 6, in figure 10, figure n, and explain our reasoning. And we're not necessarily going to go through this whole thing, but what I wanted you to do is see if you could figure out the pattern that you see in these figures. You got it, Eli?
Yes, it is.
Well, yes, it's unknown. It is X. Yeah, but Calista. So we've got 1, 1, 1, and 1 adds to 4. 1 and 2, well, that'd be 3, 3, 3, 3. 3 times 4 would give you 12. We've got 6, 6, 6, and 6, so 6 times 4 gives you 24. And then we've got 10, 10, 10, and 10 adds to 40. So like Calista said, you could either just say, I'm going to add all these yellow ones up and that'll give me the green one. Or you could say, how many of those lead away? I just need to multiply that by what each one of these branches that we see here adds up to. So anyway, it's one of those things where you just start looking around and start thinking about the patterns. But here's a way to try to do this with a methodical search, and that would be, notice that the green numbers are going up. So you ask yourself, what are some basic things that I can do to numbers to make them go up? Well, I could add something, I could multiply by something, or I could raise it to a power. And you just start your search that way. If you notice, hey, the numbers are going down, well, subtract, multiply by a negative. Just keep trying. Division sometimes will work when you're trying to make numbers go down, and find a methodical way to search for that pattern. So what we're going to do today is a little bit about geometric patterns. I mean, we've got a sight pattern here that we're looking at, but what we're using in this particular chapter is going to be mostly just sequences of numbers, trying to figure out where that pattern came from. So a sequence is an ordered list of numbers. You know, it's not just putting them in a hat and drawing them out and then saying, I'll just write this down. There's something that's happening that created a pattern for those numbers. And they're just separated by commas. So if I give you this one, the dot, 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 by the way, means something in math. 3 dots means it goes on forever. So this is a pattern of numbers. Do you know what pattern that is? Adding 3, you could do that. Somebody see a different pattern or explain it a different way. Multiples of 3. 3, 6, 9, 12, 15, 18. And that's the multiples of 3. So term of a sequence. This is the first term. This is the second term, this is the third term, this is the fourth term, because we want to be able to talk about the term that we need. So each number in a sequence has a subscript, and that subscript is used to represent the position of the term. So what we have to do, part of it today, is learn the vocabulary of sequences and series. And when we talk about terms, we always use a lowercase a. So lowercase a stands for any term that I want to have. In fact, if I add this n, that's exactly what that means. To find any term, here's what I'm going to do. But if I want a specific one, like let's say I want the 7th term, I'm going to put a sub 7 because that's subscript. So the term a sub 5 is the 5th term of the sequence. So a little bit of learning about the mathematical notation that we use. And you can see here they've got first term, second term, third term, etc. And then it gets a little weird. N minus 1. The n minus 1 term. What on earth are they talking about? They're saying we had some term, any term, and this one is one less. So that means that's the term before it. Because if this is 5, 5 minus 1 would give us the 4th term. So in our heads, we need to call this the previous term. The previous term. And once we get the notation down, when we read that, we won't even read a sub n minus 1 anymore. We'll read it off as, oh, the previous term is. So here's our a sub n. This is the term right before it, n minus 1. If you needed the term right in front of that one, you do n minus 2, and you continue on. And then this one says a sub n plus 1. Well, that means the next term, the term after, the next term. Because a lot of times we are, when we build our formulas, just going to be using a sub n. We want our formula very generic so that we can use it to find anything that we could possibly need. So on the next page, it says an explicit formula. Remember, explicit is do what you're told, here it is. It'll always work. So this describes the nth term of a sequence using the number n. We want a formula so that anybody could take a look at it and say, oh, I could get you the 75th number in this sequence by that formula. So here's how we start. We say, all right, a sub n equals, because this means any term. So to find any term, here's what you need to do. And we set up a table because this is the best way to see what's going on. And for explicit formulas, we ask ourselves, is there something easy, because the number of terms here are 1, 2, 3, 4, 5, something easy you can do to 1 to get a 2, 2 to get a 4, 3 to get a 6, 4 to get a 8, and 5 to get a 10. Something pop out at you? Eli? You just found the formula.
That'll wait.
2n. There it is. So if we want the 150th term, we're going to put 150 right here to symbolize that it's the 150th term. And we're going to take 2 times 150 and get 300. We don't need to do all of the terms leading up to the 150th term. We just need that one. This is definitely the best way to write a formula. Explicit formulas are great, but some sequences can't be written explicitly, and we are forced to do them recursively. Your homework actually tells you which way they want you to write it, whether or not they want an explicit or they want a recursive formula. So this one says, now that we know how to get one, we also need to be able to use them. Typically, this shows up on the MCAs. It says we're going to generate a sequence using an explicit formula, and the sequence has this little explicit formula. And write that a little bit bigger. A sub n equals 3n minus 2. What are the first 10 terms of this sequence? Now, this is really important. We can't just blindly start writing the numbers down. What I want you to do is learn the notation. So we're going to write a sub 1 equals, a sub 2 equals, a sub 3 equals, a sub 4 equals, because that means this is the term, the first term, second term, third term, fourth term, etc. this formula was built explicitly. That means if we want the first term, we're going to take 1 and we're going to put it right here. See what we get. So 3 times 1 minus 2. And we get 1. Then we go down to the second term and we say, well, that'll be 3 times 2 minus 2. That's going to be 4. 3 times 3 minus 2, 7. 3 times 4 minus 2 is 10. And now hopefully we don't have to do that for anymore, because hopefully we start to see the pattern. First of all, this is a linear pattern. It's n to the first, just like x to the first would be if you graphed it. This is a line. And what we're doing is we're going up each time by the slope. So we look at this and say, well, I don't want to keep doing all of this math if I notice all I have to do is add 3 every time. And after you do 3 or 4 of them and you're sure of the pattern, then you don't have to. When they give us this pattern in the book and they ask us to write the formula, it won't look like this. It'll look like this instead. And so it becomes a little bit harder because you have to think, okay, how do I take that and make it 3n minus 2? So like I said, I would look at the numbers and I'd say, oh, it's going up. And then you notice, hey, they're adding 3 every time. But for explicit formulas, that's not going to be good enough. You have to start thinking, okay, if I took this times 1, what would I need to do? If I took this times 2, what would I need to do? Times 3, what would I do? And eventually, you'd find this formula. So later on, we learn formulas to help us do this, but right now it's kind of trial and error. This says we've got a sequence with an explicit formula of a sub n equals 12n plus 3, and we just want the 12th term. So we have to do them all? No, we do. A sub 12. You just stick the 12 in there and see what happens. So what do we get? Sure do. That is a really basic thing they throw on the MCAs every year. They want to know, did you get taught how to put numbers into a formula that involves sequences? Sometimes the a sub n thing just throws people. They're like, I don't know what to do. What's this a sub n? But just having seen one now, you know this is not hard. It just means it's talking about a sequence. We always use lowercase a's when we're talking about sequences. It's just how it is. Math picks ways to do something and sticks with it. So now, recursive formulas. Recursive formulas, those are different. Those are the ones where you have to build up from the bottom turn up. So these relate each term to the term or terms before it. Term or terms before it. And it has to contain 2 parts. Bless you. You have to tell them what the first one is. If you're going to tell them, hey, to get the next one, add 3. Where's the next one? I have to know what it was that I started with. So we're going to have to tell them what that first number was in the sequence. And then after that, we give them what's called a recursive formula. A recursive formula. So you'll notice this recursive formula is a sub n equals a sub n minus 1 plus 5. It's not how I read it off in my head. I read it off this way. To find any term take the previous term and add 5. Because that's what it says in mathematical notation. If you want any term, take the term before it and add 5. Remember, a sub n minus 1 means the previous term. So I know the first term is a 2. That means the second term has to be a 7, because they said to get the next term, add 5. The next one would be 12, the next one would be 17, etc. But like I said before, to do recursive, you have to keep going. If we want the 50th term, we're doing that 50 times. You know? So it's not the best way to write a formula, but sometimes it's the only way you can think of to get it. So down here it says the number of blocks in a two-dimensional pyramid is a sequence that follows a recursive formula. What is a recursive definition for the sequence? Okay. Well, this said it was about the number of blocks. We better write down what we see for number of blocks. 1 block, 3 blocks, 6 blocks, 10 blocks, 15 blocks. Oops. 21 blocks. Now, how come I didn't sit there and count all the blocks each time? You only really have to count the new one on the bottom, right? And add it to what you're doing. That's what you're really doing here. So, 1, 3, 6, 10, 15, and 21. And they want a recursive formula. Well, we have to tell them the first one. The first one's a 1. There's 1 block there. That's what we have. And now what we want to do is figure out a way to tell them how to get to the next ones. Well, remember, I said this can be really tough, but if we put this into a table, sometimes it makes a lot more sense, and it's easy to figure out what it is we need to do. So our table consists of which number term are we talking about? And we've got 1, 2, 3, 4, 5, 6 of them here. And we're going to put those numbers for the number of blocks that we got below it. And we're going to look at our table and see if we can't figure out some way to give them a formula that involves n that would crank out these numbers. Look at the table for a little bit. Remember the numbers are going up. Think adding, think multiplying. Everybody see it? And that big hint will be think adding. And that one's going to be a little hard to describe in terms of, what do you do with the first one to get the second? Yeah. Not going to be powers. This. That's 1 plus 2. That's 3 plus 3. 6 plus 4. 10 plus 5. So here's what we have to think. This is recursive. I need to tell them something about the previous term. So they're going to do something to the previous term. What do I do to a 1 to get a 3? I add 2. Oh, wait a minute. That's n. What do you do to 3 to get 6? You add 3. Oh, it's n again. And you notice they're constantly adding the number of the term. They're adding n. So recursive can be a little hard to see sometimes. But you get it on the table and you start thinking, how do numbers go up? What do I see in the table that would make that happen? All right, down here it says, what is a recursive definition for each sequence? And then it says the hint is look for simple addition or multiplication patterns to relate consecutive terms. So we know we have to tell them the first term. We know our formula is going to say do something to the previous term. We're just not sure what that something is yet. Let's make our table. We have 6 again. We do. minus 1. So once you know where to look, not so bad. All right, let's look at this one. First term is a 5. Find any term, we're going to do something previous term. Hence this time is going to be when you can look in a different place. Recognize those numbers. What are they? They're the perfect squares. What do you square to get 4? What do you square to get 9? So this time it's n squared. N squared. You see how you have to keep investigating that table. What do I see in this table that's going to give this to me? The numbers are going up. I'm going to try addition. Addition doesn't work. I'm going to try multiplication. Multiplication doesn't work. I'm going to try powers. What is it better to use a recursive formula? I'm going to tell you, I can't stand recursive formulas. I don't like repetition. And I don't want to sit there all day and add 7, add 7, add 7, add 7, add 7. But if you only need a really small number term, then they're not so bad. So for small, position terms, meaning the first one, the second one, the third one, the fourth one, then recursive wouldn't be so bad. You just need some right at the beginning. But explicit formulas, like I said, you can find the 1,500th term with an explicit formula. So explicit formula for large position terms. My preference is I'd always like an explicit formula if I can get it, because then I can find whatever term I want, whether or not it's a small or a large number term. So we've got our little pyramids again, and this says we're going to write an explicit formula for a sequence with the pyramid, and they want to know what's the 100th term of the pyramid sequence in problem 2. I don't want to do recursive. I don't want to sit there and say add this, add this, add this, add this. I want to do explicit. So explicit means I have to tell them this is my formula involving n, not a sub n minus 1. You're not going to use the previous term. You're going to use what you have in the table. And I'm going to tell you that this one is a horrible one because it uses a fraction, and you guys are just starting off. And so it would be really hard for you to see a fraction at this point. So I'm going to go ahead and give this one to you, and we'll just talk about it. It was a really bad example for them to put in the first section. It's awful. And that's because what you would really see if you were doing this is think about distributing this. We would see that n distributes through here, and then everything divided by 2. That's a tough formula. It's going to take somebody a long time to find n squared plus n divided by 2 when they're looking. So we're just going to go with what they have. Now they want the 100th term, so what does that mean we need to do? Chuck 100 in there. And then we're going to follow the order of operations. So we'll do our 101 first, and then we can multiply everything. So 1/2 or 0.5. I've got the glasses here somewhere, so I'll punch in the stuff. 0.5 times 100, we already know is 50, times 101. 5,050. There it is. I should just leave a note for myself to replace that with something decent next year. That is just an awful formula. I tried to throw it, you guys right away. The 3A says, what is an explicit formula for 0, 3, 8, 15, and 24? This one I think we can do. This one I think we can find. Hint, powers. Yes.
Oh, Sam. Oh. Dang, I see.
Take n and square it, and subtract
Oh,
1.
now I see it.
Exactly. When somebody goes, that's what it is. Yeah, that makes perfect sense. You know. But again, it helps to get that hint of, hey, look for this. Try to figure out what this is. So that would be our formula. Oh, what did they want? They want the 20th term. Oh, I put n sub 2 instead of n squared. Man, that was good. So what's 20 squared? 400. Minus 399. Sam's man, he found that one.
Yeah, Sam's a man. Yeah.
All right.
Let's hear it to Sam. Yeah.
Sam. Because of the 36 minutes, and I wasn't sure we'd be able to get through the last piece anyway, I'm just going to say good for today. Well, there's homework.
Oh, that looks like a
And this, it's going to be one of those assignments where for some of you it's going to be a little bit discouraging, because it might take a little while for you to see some of them.
really scary.
Like I said, I used to be there too. Remember, if it's going up, try adding,
Look in the notes.
try multiplying.
So that the formula helps you find other formulas.
You're going to read ahead, Eli?
Wow.
Come back on Monday.